So in our previous lecture, we talked about block diagram reduction technique. We learned some rules that are involved in block diagram reductions and did some examples based on the same. Today, we'll study how to obtain block diagram from the given electrical or mechanical schematics. What are the steps involved and uh, the basic difference between the steps in obtaining block diagram and in obtaining transfer function. So we start understanding this part by solving an example. First, for electrical network, a simple electrical network as shown, comprising of RLC components, and then we'll move forward to mechanical system, an example of mechanical system. So let us say that this circuit comprises of a supply voltage Vs and an output voltage V naught. So in order to obtain block diagram from a given schematic, we'll first try to apply KVL to the circuit, very similar to what we did in obtaining the transfer function, but the basic difference in obtaining block diagram and in obtaining the transfer function is that if you look at this equation 1, so you on applying KVL obtain an equation Vs which is equal to IR plus L di by dt plus V naught. So instead of writing 1 upon C I dt, which we did in case of finding the transfer function, we are going to simply write in place of that term V naught. So let me show that for you because it's given here. So if you remember that in order to find the transfer function for the same network that we did in unit 1, so instead of writing this term in obtaining block diagram, we wrote 1 upon C I dt. So the basic difference in writing the KVL for obtaining transfer function and for obtaining block diagram is this term. So instead of this term, we are going to write simply V naught. So V naught is nothing but the same voltage that appears across the capacitor, and you will understand that why are we writing this term instead of 1 upon C I dt. So we call this equation as 1. Then again, V naught is nothing but 1 upon C integral of I dt. So we get two equations, and if you take the Laplace transform of these two equations, what you get is Vs equal to, from first equation is Vs equal to IR plus SLI plus V naught. And again, if you're going to take, because you are trying to obtain block diagrams, and you will in case of block diagram see elements like comparator, some blocks, feedback signals, and arrows. So that is why what we do is we will try to take all the terms carrying the same unit at one side. For example, we have Vs, which is nothing but the voltage, and then we have V naught, which is again a voltage value, a voltage unit. Then we take this on left hand side to compare with Vs. We get an expression Vs minus V naught, which is equal to R plus SL into I. If we further simplify this term in terms of I, we get Vs minus V naught divided by R plus SL. So you might now start to understand that why we have written V naught, why we have taken this as V naught instead of 1 upon C I dt. So if you see this expression, then you have Vs minus V naught. So you are going to subtract V naught from Vs, which requires comparator. So if you are going to feed a signal Vs to this comparator, then you have another signal V naught with the negative sign because you have a minus sign here. So this comparator will give you an output Vs minus V naught, which if further fed to a block with transfer function 1 upon R plus SL will provide you the output I. So this I is nothing but Vs minus V naught from obtained from comparator, then fed to 1 upon R plus SL. So this term will provide you the current I. Remember one thing, that if you are going to obtain block diagram representation, so always try to keep the input at the far left side and the output at the most right side. So for example, in this case you took Vs at the most left side, and we'll try to obtain V naught at the most right side. So Uh, Now, if you apply one more relation, if you see the relation 2, equation 2, you apply Laplace transform to it, you get a relation V naught equal to 1 upon SC multiplied by I. So this gives you the second block representation, which is nothing but I fed to the block 1 upon SC, which provides you the output V naught. Now, what we are going to do is we are going to compare the two blocks, and we are going to connect the two blocks in order to obtain the final block diagram representation of the system. So if you combine the two blocks, we get the final diagram representation, which is nothing but as shown here. So what we did is, if you look at the previous block, so this is the previous block, we picked this block and then we placed it here. Then the output from this block, which was nothing but I, is fed to this block, and this block is placed at the output of the I, this block, which is nothing but I, is fed to this block, and the output of this block is nothing but V naught. Now, in the previous block, you saw that we have one more input V naught. So this is in this particular figure shown to be floating. So no connection is shown for V naught. So this V naught should be coming from the system, from inside the system. Vs is something that is being supplied externally. That is why it will always be floating. But V naught given to comparator must be coming, because system is going to generate the output V naught. That is why the signal should be coming somewhere from the system. So this V naught is nothing but is obtained after connecting all the blocks. So this block is going to give the output V naught, and hence we are going to pick this signal and going to connect this to the comparator. So this is V naught. So this is the final block diagram representation of the given electrical network. So we have another example comprising of two loops. So you can have complex electrical networks that can be represented by block diagrams, and so I'll try to give some more tutorial questions based on them, or I'll provide you some references in the books for more questions that you can do yourself. So in this particular figure, if you look, you are again going to apply KVL in the same manner that you did in the previous example. So you have input Vs, and then current I1 that flows in loop 1. So the loop 1 comprises of a resistor R1 and a capacitor C1. So I1 will be flowing through resistor R1, but in case of the capacitor C1, the current that flows through capacitor C1 is I1 minus I2. So if you apply KCL at this particular node, since you already learned about these things, you say that this current is I1, and you assume that this current is I2 because current I2 flows in the second loop. So that is why this current will be I2. So in this particular branch, you're going to have I1 minus I2, and that is why the current that flows through capacitor will be I1 minus I2. Thus, if you apply KVL now to this first loop, what you get is the equation Vs, which is equal to I1 R1 plus VC1. So we are not going to write 1 upon C1 integral of I1 minus I2. Had we been finding transfer function for this circuit, then we would have written in place of this element, this component, 1 upon C1 I1 integral of I1 minus I2. But since you're obtaining block diagram, so you are supposed to write this as VC1. And again, if you apply if you see VC, what is VC1? VC1 is the voltage that appears across capacitor C1, which is nothing but 1 upon C1 integral of I1 minus I2. Likewise, if you're going to apply KVL to loop 2, in that case, you get VC1, which is the voltage that appears across C1, and then you have a voltage drop across R2, then a voltage that appears across C2. So you get VC1, which is equal to I2 R2, plus V naught or Vc2. Vc2 is nothing but the output voltage V naught. So the voltage that appears across C2 is V naught. So again, what is V naught or Vc2? Vc2 is nothing but 1 upon C2, the current that flows through C2, which is nothing but I2. Now because you don't have further current division at this particular node, so this branch is open. So you have no more components connected further. That is why the current I2 that flows through R2 will completely flow through capacitor C2, and no part of that current will go on right side because there is no more further circuit given. So now if you apply Laplace transform to each of these equations, from equation 1 you get Vs equal to I1 R1 plus Vc1. So we call this equation as A. From equation 2 you get Vc1 equal to 1 upon Sc1 I1 minus I2. And again from third equation you get Vc I2 R2 plus Vc2. And from fourth you get Vc2 equal to 1 upon Sc2 times I2. So A, B, C, D are the Laplace transformed equations corresponding to equation 1, 2, 3, and 4. So if you want, you can compare this particular example with the example. So I think we didn't find the transfer function of this circuit in the previous unit. So there is no problem. You can try yourself finding the transfer function of this circuit using the same methods that we used in unit 1, and compare those methods with the methods that are involved here. So again, using these four equations, we'll try to represent them, each of these equations, into block format. So if you look at equation A, so you have voltage Vs and then Vc1. So these two voltage will be compared. So all the terms with the same unit will be taken on one side. So we are going to have Vs minus Vc1 after taking Vc1 on the left side, and from this we can obtain the current I1, which is nothing but Vs minus Vc1 upon R1. So this can be obtained in this manner. So this equation can be reduced to I1 equal to Vs minus Vc1 upon R1. So corresponding to this, we'll be having a block diagram representation for this particular expression as Vs fed to the comparator subtracted by the term Vc1. So for this we'll be having a comparator, and then the output from that comparator will be fed to a block 1 upon R1 in this manner to obtain the current I1. So using the same expression, what we did is we used a comparator in order to subtract Vc1 from Vs, and then we multiplied again 1 upon R1 in order to give the final current, which is I1. Now if you look at equation B, so equation B was Vc1 upon 1 upon Sc1 I1 minus I2. So this is what we obtain in equation B. So using this equation we get the expression, we rewrite this here, and then we try to obtain the block representation of the same. So it says that you have two currents, so I1 and I2. So because I2 is being subtracted from I1, we will be providing these two currents to the comparator in this manner. So and then again multiplying it by a block 1 upon Sc1 to give the voltage value Vc1. So I guess if anybody has any problem, is not able to understand, you can stop me in between. You can ask me questions. You can ask me questions on the mic or post it in the chat box. Is it clear to all? All right. So equation B gave us this block representation, and again from equation C, which was Vc1 equal to I2 R2 plus Vc2. So you again have two voltage values, Vc1 and Vc2. So we're going to take this on one side, and since you see that Vc, look, this always goes in a systematic order. Like from first equation you obtain this expression, then you at this particular representation had a component I1 on the rightmost side, which must be fed to another block. So if you look at the second block, so I1 is being fed to comparator, fed to this block, then you have Vc1. Again, this Vc1 is not the final output. So final output is Vc2. So Vc2 in the final representation of block diagram must be on the far right side, and thus we will be having additional blocks at the right side of Vc1 So for that, what we do is VC1, we're going to take these two voltage values at one side. So VC1 minus VC2 upon R1, sorry, it should be R2. Slight correction here. Alright, so I2 gave you VC1 minus VC2 upon R2, and for this you have this particular block representation. So you have VC1 minus VC2 fed to the comparator. Since VC2 is being subtracted, you have a minus sign here, and then this is multiplied by the the gain or the transfer function upon R2 in order to give you the current I2. And again, you have Vc2, the final output, which is nothing but I2 multiplied by the gain 1 upon Sc2. So we're going to feed this I2 to a block 1 upon Sc2 in order to give you the output V0 or Vc2. Now we are going to use all these three block representation in order to find the our final block diagram representation as shown. So if you look at this particular figure, so these are the four block representation we obtained from ABC equations A, B, C, D. So we are going to connect them. Since Vs, so we use this and represent here, and then I1 is being fed to this comparator, so we connect this here, and the output from 1 upon SC1 block is VC1, which is then fed to this particular comparator, so we connect this here, and then we have 1 upon R2 here, the output is I2, I2 is being fed to 1 upon SC2 to give you the final output V0 of VC2 here, and then all the feedback are connected accordingly. So VC1 is floating and was supposed to be connected at this particular point. So we connected this here. So VC1 is connected in this manner. And likewise, you have I2 floating, which is something internal to the system. And this I2 is coming from this particular point, and thus this is why we connected this particular point at I2. Likewise, VC2, which is V0 output, and we have this particular value at the input of the comparator here, and thus this will also be connected at this particular point like this. So this is the final block diagram representation of the electrical circuit shown. Now we talk about the mechanical systems. So since now till now we have been talking about examples that we did in unit 1 in order to find the transfer function. And I use this example because to give you to allow you understand the difference between finding the transfer function and obtaining the block diagram representation. So again, in this particular case, we're going to obtain the FBD. So you always have to apply the basic governing rules in network or mechanical system. So for electrical systems, electrical network, you have KVL and KCL. For mechanical system, you have Newton's laws of motion or D'Alembert's principle. So if you apply D'Alembert's principle mass to mass m1, so this is the free body diagram where you apply force. F is the input provided to M1, and the resisting forces that exist here will be because of spring K1, because of friction FV1, because of dashpot FV3, because of spring K2, and because of mass. So there are 5 resisting forces that will exist after force is being applied to this particular mass. And notice that we now again in the same way we are going to take variables. So instead of the thing that we did in finding the transfer function, we are going to assume these two forces as Fk2 and Fd. So if you look at the problem we did in finding the transfer function, so here is the problem. So what we did here is we, instead of writing the force, we wrote the expression like this for Fv3. So this was the expression for Fv3. And we had another expression corresponding to K2, which is K2 x1 minus x2. Instead of these two expressions, I mean the K2 and so instead of K2 x1 minus x2 and Fv3 d by dt of x1 minus x2, what we did here is we wrote Fk2 and Fd. So very similar to what we did in electrical circuits. And you might now be confused that why are we taking forces, why are we replacing these two terms only, why not this term? So are if you understood the case for electrical circuit, we did this because if you look at this circuit, we have an input Vs and output V naught. So in our block representation, we must be having Vs at far left side and V naught at far right side, and whatever variable that exists within the system should be shown internal to the block diagram. So this was, if you look at this block diagram, so Is is internal to block diagram, while at the most left side is Vs and at most right side is V naught. So we try to obtain, or we try to uh, avoid these variables which are internal to the system to be shown at the far left or far right side, and that is why we try to write. In fact, if you look, the current that is flowing in through the circuit is I, and that flows because of the supply voltage, the difference of the supply voltage and the voltage that exists across the capacitor. So voltage across the supply and across the capacitor causes the current I to flow through RL. So the flow of current has two voltages existing on either side, and that is why we, instead of having the same thing exists here. In case of mechanical circuit, if you look, since you have x2 is the output and x1 is also displacement but is not the output, so since these two components will be having both the expressions x1 and x2, and that is why instead of writing them as k2 x2 minus x1, or corresponding to fd d by dt of x2 minus x1 or x1 minus x2, we wrote it as fk2 and fd. So this is done in order to have the comparators involved in the block diagram representation, because if you're not going to show this in this manner, you're not going to have comparators being shown into the block diagram. So the block diagram that you will be obtaining, if you're not going to use these terms, will not have comparators in it. That will be more simplified form of representation. So if you equate these two, the acting and the resisting forces, you get an expression like this, which is again slightly different from what we obtain in case of transfer function. So the difference is here. Now if you take the Laplace transform of this particular expression, you get f equal to k1x1 plus s fv1x1 plus fk2 plus fd plus s square m1 x1. And from this we take all the terms involving force. So we have f, fk2 and fd on left hand side or at one side, and then we'll try to obtain expressions in terms of x1. So we took the forces at the left hand side and we have expression with x1. So x1 from this expression gives you this value. So what this shows is that you're going to feed the input f to a comparator, subtracted from two more values fed to the comparator, and then that will be multiplied by the block 1 upon k1 sv, this expression, to give you x1 like this. So we have a comparator, we fed f as input to it, fk2 is shown here, fd is shown here. So both are taken with a minus sign because you have a minus here, and then this is being multiplied by the gain or the transfer function 1 upon this expression as shown here. This will give you the output x1, which is displacement corresponding to block 1. Now if you use equation 2, so we assume fk2 as force, which was nothing but k2 x1 minus x2. So if you look at this circuit, what is fk2? Fk2 is nothing but the net expansion, which is x1 minus x2 multiplied by k2, which is fk2. And likewise, you will be having fd, which will be equal to fv3 d by dt of x1 minus x2. So both of them are written here. So fk2 is k2 x1 minus x2, and fd is fv3 d by dt of x1 minus x2. So if you take Laplace transform of these two terms, you get this value, and from this value you get the block representation with x1 and x2 fed to the comparator, x2 having a negative sign, and that is why a negative sign is taken here, multiplied by constant k2 to give you the final output fk2. Likewise, you will be having expression fd equal to, if you take Laplace transform of this expression, this is fd equal to sfv3 x1 minus x2. Notice that this fv3 is not a function; it's a constant. It's a coefficient of damping related to friction. While this fd is the force, frictional force, the dashpot, the force that is exerted because of the dashpot. While this is coefficient of the damping coefficient, not friction, damping coefficient. So we have this force represented given by this particular term, and from this we obtain the block representation comprising of comparator x1 and x2 with plus and minus sign fed to the gain fv3 to get the output fd. So we still are not having the final output. The final output in the circuit in this schematic is x2. So we'll try to obtain a block representation which will be having at the far right side the term x2. So if you look at these blocks, you didn't still got x2 except for this term. So this is nothing but a floating point which is which will be taken from a feedback of the output x2. Now if you draw the FBD of mass m2, so fk2 and fd becomes acting on mass m2, while the other resisting forces that exist on m2 will be these terms. So I'm not going to into details of how these are going to come, because this is already been discussed in unit 1, and if someone of you have some people have problem understanding this, can refer to unit 1, the lectures on unit 1. So if you are going to equate the acting and resisting forces, you get this expression fk2 plus fd, which will be equal to all the resisting forces given as follows. And if you're going to take the Laplace transform, you get these converted into this form. So all the forces will be expressed in terms of capital letters like this, while this is not capital because this is not force, rather the coefficient of damping or friction. And again, simplifying it further, you have the x2 taken as common, and then you get x2 as fk2 plus fd divided by this term, and from this you obtain the block representation having comparator fed with two signals fk2 and fd. So you don't have a negative sign now here, so that is why you're going to take positive signs. Since both of them are positive, that is why this comparator has its input with a positive sign. So these two forces will be summed in the comparator fed to a gain with 1 upon this term. So this is shown here to give you the output x2, which is nothing but the final output. And now again connecting all the blocks that we obtained to represent the final representation. So this was obtained from the first expression, second, third, and fourth. So if you connect all these blocks, so this block is shown here, and we connect this to this particular block. So now Fk2 in this particular block, if you see Fk2, which is force that is being produced because of a spring K2, is also being fed here, while Fd is coming from this point. So the signal will be taken from this particular point and fed here. Likewise, a signal at Fk2 will be taken and fed here. So we try to represent this in this manner. So you have x2 given to the comparator, x1 coming from this block is fed to the comparator, multiplied by k2 will give you fk2. This fk2 is being picked here and then fed back at the first comparator at this particular point. Likewise, you will be having second block where x1 and x2 are being fed to the comparator. So this particular point corresponds to this point as well. So we connect this point to SFV3. There is this block to provide FD. So this point is fed to SFV3 to give you the output FD, which is being fed at this point. So it's shown here. Now you have these two values, FD and FK2. They are summed together at the comparator and then fed to this block to give the final output X2. Now we still have a floating point X2, so this should be connected to the final output X2 in this manner. So this is the final block representation of the mechanical system shown. And if any one of you have any problem in at any place, so you can ask me questions.